the use of technology in astronomy has advanced to the point where we can now detect the presence of worlds beyond the solar system. Here's a photograph of 4 of them. The discovery of these worlds is changing the way that we think about our place in the solar system, in the galaxy, and the universe at large. My task today is to summarize to you this ongoing revolution in astronomy and also describe to you what to expect in the next 10 years. So let's begin with a definition. What are exoplanets? Exoplanets are planets found outside of our solar system, orbiting other stars. For thousands of years, all we knew about were the 8 planets orbiting our sun. This changed in 1995 when Swiss astronomers from Geneva discovered the first example of an exoplanet orbiting a sun-like star. Just barely 10 years later, 2 groups of American astronomers made the first detection of infrared light coming from the atmosphere of an exoplanet. And just last year, the Kepler Space Telescope of NASA announced more than 2,000 exoplanet candidates, most of which we think are real. And if they are real, then we have gone from knowing about 8 planets to knowing about 3,000 planets in less than 20 years. Think about that. In a few years, there will be a space telescope dedicated to the study of exoplanets, led by Switzerland, and it will launch in 2017, and this is based at the University of Bern. Now, this is a graph of the number of confirmed detections as a function of the year of discovery. The first thing you notice is the exponential growth I just described to you. The second thing you notice is that there are various methods of detection coded by color. Your eyes already tell you that there are 2 main methods, the radial velocity method and the transit method. I will spend some time in the talk telling you about these methods. The point is that these 2 methods measure the radius and the mass of an exoplanet rather accurately, which means you can figure out how dense these things are. And when you do that, you can figure out that there are 2 broad classes of exoplanets. There are the ones that are gas giants. These are big and fluffy, much like Jupiter and Saturn are in our solar system. And like their name suggests, these are like giant balls of gas. The second class of exoplanets are smaller and denser, much like Earth, Mars, and Venus are in our solar system. Let's talk about some highlights of exoplanet discoveries. So one of the most astonishing discoveries is that of a class of exoplanets known as hot Jupiters. These are gas giants, much like our Jupiter, with similar masses and radii, but they're located almost 100 times closer to their star than our Jupiter is. So the temperatures in these things are scorching. You're talking about 1,000 to 3,000 degrees. The other thing that's really surprising about hot Jupiters is that when you do find them, they tend to be loners. They tend to be found by themselves, far away from other exoplanets. This is not the case for rocky exoplanets. When you find rocky exoplanets, they tend to be found in multiples, up to 9 rocky exoplanets orbiting the same star. When you count up these rocky exoplanets, you come to the conclusion that roughly 10% of nearby stars have at least 1 rocky exoplanet. So nature has a way of forming, efficiently and robustly forming exoplanets that we do not fully understand yet. Now let's talk about the methods of detection. The first method is the radial velocity method, which I already described to you. So most of us in the room have this picture in our head of a static sun at the center of the solar system with the planets orbiting around it. This picture is not quite correct. A more correct picture in the example of an exoplanet orbiting a star is that they orbit around a common center of mass, such that from the perspective of the astronomer, the star wobbles back and forth. As the star moves away from the astronomer, the light gets slightly redder. As it moves towards the astronomer, it gets slightly bluer. And so by staring at the spectral lines in the atmosphere of the star, we can measure what this wobble is. And this is related to how massive the planet is. Therefore, this method is very good for measuring the mass of the exoplanet. And the group that does this the best in the world currently are our colleagues in Geneva. The second method is the transit and eclipse method. So the reasoning is that if you look at enough stars in the sky, some fraction of them will have exoplanets. If you look at enough stars with exoplanets, some fraction of them will have exoplanets in edge-on orbits, such that at a certain moment in time, the exoplanet goes in front of the star, blocks out some of the light, and causes this little dip in the light you see in orange, known as a transit. Now, if you wait long enough, the exoplanet swings around, goes behind the star blocks out the light from the exoplanet, you see an even smaller dip called an eclipse. Now imagine an exoplanet with an atmosphere with one major molecule, say water. There are certain wavelengths at which water is opaque to starlight. Therefore, the exoplanet appears a little bit larger. There are certain wavelengths where water appears transparent to starlight, and therefore the exoplanet appears a little bit smaller. So the reasoning is that if you make measurements of transits across a range of wavelengths, you can actually figure out what the major molecules in an atmosphere are. Here's a real-life example of a transit and an eclipse. The first thing that you will notice is that the eclipse is much shallower than a transit, just as I described. Check out the numbers on this plot. Look at how small the numbers are. This is a very hard measurement to make. The second thing you notice is that if you zoom in on the data between the transit and the eclipse, you see this rising sinusoidal trend. This trend is direct confirmation that this picture I just showed you is correct, because what you are seeing are the phases of the exoplanet as it swings around from transit to eclipse and shows you more and more of the bright day side, causing an increase in the light and the increasing trend that you see in the data. The third thing you should take away from the graph is that if you can measure the eclipse of an exoplanet, you know exactly the moment in time when it only shines in the light of the star. Therefore, you can subtract out the light of the star, you end up only with the light of the exoplanet, and using this information, you can construct a map of the exoplanet, which I show here. This graph shows you the infrared light from the exoplanet as a function of longitude. 0 on this graph corresponds to noon on the exoplanet. The fact that the exoplanet is brightest not at noon, but at some location shifted away from noon, is direct evidence for the existence of atmospheric winds in the exoplanet. Why these winds exist and why they have the structure they do can be explained by using computer models known as simulations. So the exercise is you take a climate simulator for Earth, you take it apart, you put it together, put it back together, and you use it to predict what the temperatures and the winds are on an exoplanet. To a very good degree, theory and data agree rather well, but there's a lot more work to be done. So let's pause and take stock. In less than 20 years, we have gone from discovering the first exoplanet to actually being able to characterize their atmospheres. That's a lot of progress in a very short amount of time, and I find it nothing short of remarkable. So let's go back to this graph. I've told you about transits and eclipses. Just before the eclipse is when the exoplanet shows you most of its light. If you make multiple measurements at this location, across a range of wavelengths, you can construct a spectrum of the exoplanet atmosphere, an example of which I show here. So this graph shows you the infrared light at the position just before eclipse as a function of wavelength. And if you analyze this spectrum carefully, which one of my team members does for a living, you can actually figure out what the major molecules in the atmosphere are. So in this example of hot Jupiter, which is the same hot Jupiter I've been talking about, there is evidence for carbon dioxide, water, and methane. So you can start to do some atmospheric chemistry. So I've spent a lot of time talking about gas giants. How about Earth-like exoplanets? Because most of us in the room are probably interested in the search for life, at least the search for life as we know it. The challenge is that the two methods I just described to you are not easily extendable to exoplanets that are smaller and further away from the star. One solution to this challenge is to shrink the star as well. So instead of looking for Earth-like exoplanets around big sun-like stars, look for Earth-like exoplanets around smaller, dimmer stars that we call M stars. One virtue of hunting for exoplanets around M stars is that the range of distances where liquid water can exist on the surface of a rocky exoplanet is much closer to the star and is compatible with what you expect to find. The big elephant in the room that some of my colleagues don't like to talk about is that we want to search for life, but we actually do not have a working definition for life. It's really hard to search for something we can't exactly define it. So one of the big unanswered questions in our field is, what does the term habitable actually mean for exoplanets in general? So let's start to close by talking about the future of exoplanet research. In my opinion, there are 3 goals we should be working towards. The first goal is to actually uncover the diversity of atmospheres actually found in nature. So what fraction of exoplanets have atmospheres? What are their compositions? What are their compositions relative to the star? These are questions we all want to answer. The second goal is to develop novel technologies for not just discovering Earth analogs, meaning Earth-like exoplanets around sun-like stars, but also characterizing their atmospheres. These first 2 goals are experimental in nature. The third goal is more theoretical, which is my expertise. So I have given you a hint that you can adapt climate simulators to study the atmospheres of exoplanets. But because these climate simulators were designed for Earth, they contain many Earth-centric assumptions that you do not necessarily want to apply to exoplanets. So the challenge and the next step is to design exoplanet-centric climate simulators and use that to predict what you see in exoplanets. And this is something that my group at Bern will concentrate on for the next 5-10 years. One of the things we specialize in is using the cards in video game consoles to do this. So ask me about this at the coffee break. The biggest question that all of this research is trying to ask, which I'm sure all of you in the room have asked at one point or the other, is, are we alone? This is not a very specific question. A more specific question is an Earth-like exoplanet around a sun-like star the only possible cradle for life in the universe? This is a very exciting question, but I would argue one that we are not quite ready to answer yet. Instead, we should work on a more mundane but no less important question, which is, what are the general conditions for habitability? Meaning that if you went out and you found life elsewhere in the universe, would you actually be able to recognize it? And with these thoughts, I thank you for your time.
Thank you. Thank you. Thank you. So, I know I shouldn't ask a scientist this, but how many of those Earth-like planets do you think there are in the universe? Can you just make the calculation? 100 billion stars in the galaxy times 100 billion galaxies in the universe times what, 1 or 2 Earth-like planets?
Right. So I could answer that question. I could also answer the question if you ask me, what are the chances of finding life elsewhere in the universe? And I would say that my answer is that there are on the order of 100 billion stars in the galaxy. And if 10% of them have at least one rocky exoplanet, which is what they are finding with Kepler, that's 10 billion. And if life is a 1 in million occurrence, that still gives you 10,000 in the galaxy. And that's just our galaxy. So if you look at other galaxies, there are plenty, plenty more. And so if I don't believe that we are the only example of life in the universe, that would be the biggest cosmic joke played upon us.
Great. Thank you.